10.4, Norton and Thevenin's theorems. They're actually, we've seen this lecture before. That's why we can move through this lecture pretty quickly. We've seen this before in electronics, but now it's going to be written out in a more generalized form. So, generalized Thevenin's theorem says, given a linear network of across variable sources, through variable sources, and impedances, the behavior at the network's output nodes can be reproduced exactly by a single across variable source, VE, in series with an impedance ZE. So we're saying you can take the whole linear graph and you can rewrite it as being a source, a cross variable source, so where this is generalized across variable VE, in series with an impedance, an equivalent impedance. Pretty cool. So in order to determine what this is for a given linear network, or in our case, a linear graph, we need to find VE and ZE. So determining ZE is pretty easy. The equivalent impedance, ZE, of a network is the impedance between the output nodes with all the inputs set to 0. Setting an across variable source to 0 means the across variable on both its terminals are equal, which is equivalent to treating them as the same node. We would have called this in electronics, we would have said that's shorting out across variable sources, or shorting out voltage sources. Setting a through variable source to 0 means the through variable through it is 0, which is equivalent to treating its nodes as disconnected. We would have said that's open circuit in electronics. So that's how we determine ZE, the equivalent impedance. If we want to determine VE, the equivalent across variable source, it's the across variable at the output nodes of the network when the network is, the output nodes are left open or disconnected from a load. Determining this value typically requires some analysis with elemental continuity and compatibility equations. You can use impedance methods like we've used in this chapter, and specifically I'm going to recommend we use, if possible, the methods of 10.5 to find out what the VE is. So we haven't got to 10.5. We'll do that on Monday, and it'll be the end of this chapter. Good, so that's the Thevenin. The Norton theorem says, given a linear network of across variable sources, through variable sources, and impedances, the behavior at the network's output nodes can be reproduced exactly by a single, so this is exactly the same as Thevenin so far, but this time it's a through variable source, FE, in parallel with an impedance, ZE. So that looks like a through variable source with generalized through variable FE, and in parallel with an equivalent impedance, ZE. So that ZE is the same ZE as the Thevenin's equivalent impedance, so we know how to find that already. Determining FE, the equivalent across variable source, FE, is the across variable, across variable. I went through and I fixed, these all said current before, and I fixed it to the wrong thing. Through variable source. Wow. Great correction. And I was also wrong in this last sentence here. These are the only three places, though, because there were only three that I replaced. But I replaced them with the wrong thing. So go me. In your notes it says current. Yeah. It should say through variable source. Current source is what it is in the case of an electronic circuit, right? Current source. So, yeah. Great. So it's the equivalent through variable source, FE, is the through variable through the output terminals of the network when those output terminals are shorted or collapsed to a single node. determining this value typically requires some analysis with elemental continuity compatibility equations, preferably using impedance methods. Converting between Thevenin and Norton equivalents. There's an equivalence between these two network models that allows one to convert from one to another with ease. That's a very awkward phrasing. The equivalent impedance ZE is identical in each and provides the following equation for converting between the two representations. So if we want to convert between these two, we can say that the equivalent across variable is equal to the impedance times the equivalent through variable source. So if you have Norton and you want Thevenin, you can plug in FE and ZE and get VE. If you have Thevenin and want Norton, you can plug in VE and ZE and solve for FE. Let's do a quick example. It'll just take a moment. We actually did this example back when we were doing electronics, but we'll look at it again. For the circuit shown, find the Thevenin and Norton equivalents. So the first thing we can do is look at a linear graph. And we've got ground here, maybe. Ground, and we've got a voltage source, Vs. We've got a resistor, R1. And we've got another resistor, R2, which is the output resistor. This is where your output is coming out of. So from the node between R1 and R2, and then here. And we're going to use the same ZE in both. So we'll solve for ZE first. Set the sources equal to 0. That means that the cross variable source essentially collapses to nothing, right? And you have R1 and R2 in parallel now. And so we can say that ZE parallel. So ZE equals R1, R2 over R1 plus R2. And that's part of our answer, right? If we want to find VE for the Thevenin equivalent, then we need to solve for what the cross variable will be between these output nodes. And we can see from the location of those nodes that VE is equal to, since it's a voltage source, we can use the non-script VE. And that's just going to be the voltage across R2, right? VR2. Which we could use, we could go through and write out our full analysis and solve for what the relationship is, but we have this really nice cross variable divider rule, or voltage divider rule, which we're going to use. R2 over R1 plus R2 times Vs. So that's our solution, right? That gives us our VE. So our Thevenin is done. And now we just need to do the Norton, right? And the Norton uses the same ZC, so all we need to find is FE. We could use this little conversion formula here. We could use that to say, oh, okay, FE is just VE divided by ZE. But let's actually look at, it's a little bit more difficult to interpret for most people, what this looks like when you short out this last the output terminal. So if you short this out, that means you're connecting those two together, and R2 collapses down to nothing. And it's a little bit hard in a linear graph to see what to do at that point. So what I want to do is suggest that we'd look at it like this. we have our source, Vs, and R1 is still there, but now it's going to go to essentially to ground, because these two nodes are going to be connected together, shorted together. But if we make it go all the way to ground, we're going to lose this little bit of wire that we stuck in, right, to short it. I mean, we're thinking in electrical terms here, but I think that's useful to do. So I'm going to just put the node right here, and then just put like a little baby connection in between here. We typically don't do that. This is like a fake element. Wire element. It's essentially just like extending that node up. But what we're going to do is we're going to say what we want to know is what is the through variable through that. So Fe is equal to whatever that through variable is. And if I look at a little continuity equation there, whatever that through variable is going to be whatever through variable R1 sees, right? So it's going to be equal to I R1. So I sub R1, right? I sub R1, where I is the current going, IR1 is the current going through R1. And if you want to know what the current is going through R1, you look at what the voltage is applied to it, which is Vs, and you divide it by the resistance R1, just from Ohm's law. And that is our equivalent through variable source. That's also true. You can go back and check easily if this equation is true, but I won't keep you. It's the weekend, but do so. It's pretty nice to see that this formula does work out well. So. I very rarely lie to you, but it's good to check anyways. All right, have a good weekend.